Hello, can everyone hear me? Okay, thank you. So today will be our last tutorial. Your final exam will be on Thursday, it's very soon. We will try to cover all questions about discrete distributions today. And tomorrow I will hold a review session from 9 a.m. to 11 a.m. It will focus on problem solving. I will not have like review over the concept separately in the beginning, but I will try to remind you of some important concept as we solve the problems. The session will also be recorded. I believe that tomorrow evening, John also hold a review session. And then on Wednesday, Ahmed also hold a review sessions. And I think we will go through different questions in each review session. For my session particularly, if you go to the Google Drive that I used to upload my tutorial notes, I also uploaded the question for the review session, so you can take a look. The question was focusing on the material after the midterm. So it is about like PMF, CDF, conditional probability, discrete random variable, important discrete distribution, and also one combinatorial proof question. Okay, it's 2:10, so I will jump in the tutorial for today. We will have to go through all the important discrete distribution. The first one is Bernoulli. Bernoulli distribution is used to describe the output of an experiment where you have exactly two possible outcomes. For example, let's see, if you toss a coin, then you only have two possible outcomes, head or tail. We don't consider the case where the coin is like standing and don't have any result. We only consider like deterministic result. So in that case, there are only two possible outcomes, head or tail. And let X denote the outcome when tossing a coin. We say that X follow a Bernoulli distribution. And similarly, for example, if you roll a dice, it depends on how do you look at the experiment. For example, if you look at that when you roll a dice, and the outcome you can get is 1, 2, 3, up to 6, and X denote outcome of rolling a dice, then X does not follow a Bernoulli distribution. However, if you look at rolling a dice and your outcome is getting even or odd, then in this case, your possible outcomes is only 2. And let X denote whether we get even number when rolling a dice. Then in this case, X follows a Bernoulli distribution. So that is for Bernoulli. Let's see, even odd, yes. If you have a sequence of Bernoulli trial, then the number of success in n Bernoulli trials, follow a binomial distribution. So example is when you toss a coin 3 times, and let's say that the coins is fair, then probability of getting head equal to probability of getting tail at each trial is 1/2. Then in this case, you have n equal to 3 and denote the number of trials. And P is 1/2. P is the probability of success, and it depends on what do you define as success. Let's say I want my success to be hit. Like if I toss a coin and I get hit, then I consider that my success. Then the probability of success will be 1/2. Then in this case, X is number of hits that I can get when I toss a coin 3 times. I say X follow a binomial distribution with n equal to 3, number of trials equal to 3, and probability of success at each trial is 1/2. So that's what it means by binomial distribution. And we have to realize that Bernoulli distribution is a special case of binomial distribution. So Bernoulli with parameter P is just binomial with n equal to 1, which means the number of trial is equal to 1, and probability of success in each trial is P. So they represent the same thing. When you toss a coin 1 time and X denote whether you got head or tail, X follow a Bernoulli trial. Then it is the same as saying you have 1 trial, and then probability of success is just the same probability of success in Bernoulli. Does this make sense? And another thing is, if you have 2 Bernoulli random variable, if you have X is Bernoulli, and then you have Y is Bernoulli, and let's say they have the same probability of success, we call it P, then X plus Y is a binomial distribution. Let's say X plus Y equal to some random variable Z, then Z will have binomial distribution. Number of trial will be 2, and probability of success in each trial is, sorry, not 1/2, I mean P. Like this P refer to the P that you got here. Because if you think about it, X is Bernoulli with parameter P, which means you do the experiment 1 time. And you know that the probability of success when you do this experiment is P. Similarly, here you do the experiment 1 time, and the probability of success is also P. Then if you add the number of success here and the number of success here, you will have the total number of success when you perform 2 trials, where the probability of success in each trial is P. So that's the way to intuitively understand it. In upper year courses like 256, you will actually have to prove this. Let's see, next one. Let's talk about Poisson distribution. Because when you have X follow a binomial distribution with n trials, and probability of success is p. When you have n is large and p is small, how large and how small, I believe you covered that in the lecture. Then you can have x approximated by a Poisson distribution with parameter lambda equal to n times p. And what does this lambda represent? It represents the average number of occurrence of some event. If you let x denote the number of accidents on the highway in 1 hour, then lambda will represent the average number of accidents on the highway in 1 hour. So the lambda here just means the average, the mean. And this is the only distribution that I think you should remember its PMF. We say f of x equal to e to the power of negative lambda, lambda to the power of x over x factorial. I don't think you should remember the PMF for any other distribution because it can all be think about intuitively based on combinatorics perspective. But for Poisson, I think you should remember its PMF. There are two more distributions we have to talk about. The next one is geometric distribution. So the number of trials we have to do until we got the first success. This one follow a geometric distribution with parameter p, which means that the probability of success in each trial is p, then the number of trials we have to do until we get the first success will follow a geometric distribution. And closely related to it is negative binomial distribution. There is a number of trials until the rth success. We say that it follows a negative binomial distribution with parameter r and p. R is the number of desired success that we want, and P is the probability of success in each trial. So based on the description, we can see that a geometric distribution with parameter P is just a special case of negative binomial distribution where R equal to 1. And again, if you have two random variable x and y, each of them follow a geometric distribution with the same probability of success, and you add them together, you would get a random variable z, and z follow a negative binomial distribution with r equal to 2 and probability of success equal to p. Why is that? Because if we think about it, x denotes the number of trials until the first success. So we have a bunch of trials until there is a first success. And we denote the number of trials here by x. And similarly, Y is a geometric random variable. So Y also denotes the number of trial until the first success. If we add X and Y, then we would have the total number of trial until we get the second success. Because if you kind of append them together, this is the first success. And then here, all of them are failure until this is the first success in the Y. But then if you append them together, this would be considered as the second success. Then in total, we have X plus Y is the total number of trials until we get 2 success, where probability of success in each trial is P. So that's why it follows a negative binomial distribution with these parameter. One last thing, hypergeometric distribution. Let's say you have m black balls and n white balls, and you sample r balls out of it. So out of m plus n balls in total, you sample r balls. So let X denote the number of black balls out of the R balls that you sample. Then X follow a hypergeometric distribution. Similarly, if X denote the number of white balls out of the R ball that you selected, X also follow a hypergeometric distribution. Any question about whatever I just go over? I think the most mistake that students make is they cannot distinguish between binomial and negative binomial. They are very different if you think about the meaning of it. Here, the number of trials can vary, and your goal is that you hit R success. However, for binomial distribution, you have fixed number of trial, and the number of success are what you are interested in, and like it can vary. If there's no question, I will let you work on question 1 in 5 minutes. Let me know if you have any question. Yeah. Okay. Okay, so here we are interested in the number of cars that got stolen. So we will let X denote the number of stolen cars during a night. Then we will have X follow a binomial distribution. The number of trials here is the number of cars that we have. Because think about it, we have a bunch of cars, and then each car is one trial, whether it got stolen or not. So we will have n equal to 12, and probability of success, because we are interested in the number of cars that got stolen. So stolen is success. And the probability of a car got stolen is 10%. So probability of success is 0.1. So that's all I need you to know about the distribution. From here, you will see that we basically just use what we learned in previous chapter. For the first one, we want to find the probability that no car is stolen, which means the number of stolen cars is equal to 0. We have 12 cars. And we want none of them to be stolen. So out of 12 positions, I choose 0 position to have a stolen car. And then 0.1 is a probability that a car getting stolen. We have 0 car. And then other cars, they are not stolen. And probability of not getting stolen is 0.9. And it applies for 12 cars. So this would be the final answer for part 1. For part 2, we want at most 2 cars are stolen. At most 2 means less than or equal to 2. The number of cars that got stolen cannot be a negative number, right? Because when you start counting, the minimum of objects that you can count is 0. So the minimum value for X is 0. And then you want it to be less than or equal to 2. So you just add up to 2. So 1 is less than 2. So we want it. 2 is equal to 2. So we want it. 3 is greater than 2. So anything from 3 and above, we don't want it. The first expression is what we calculated in part 1. I just bring it down. The second one, I want that exactly 1 car to be stolen. So out of 12 cars, I choose 1 to be stolen. And the probability of being stolen applies to 1 car. And probability of not being stolen applies to the remaining cars, which is 11. Similarly, I want exactly 2 cars to be stolen. Out of 12 cars, I choose 2 to be stolen. And the probability of getting stolen applies to 2 cars. Not stolen apply to the remaining car. And if you pull in your calculator, you will get the final answer. We do the same thing for part 3, at least 9 cars. Complement law. Yeah. So here you can do 2 ways, like the students say. You can use complement laws. Or you can just do it directly. If you do it directly, you will have to add up probability X equal to 9 up to probability X equal to 12. If you use complement law, the complement of X greater than or equal to 9 is smaller than 9. And here, X denotes the number of stolen car. So the number of stolen car have to be an integer. You cannot just steal like half of a car. So we will get this smaller than or equal to 8. So you can do either way. And then for each of the probability, you do the same thing with what I did in part 2. Just out of 12 position, choose how many car to be stolen, and then take the probability of being stolen applies to that number of car, and the remaining applies a probability of not getting stolen. Any question about this one? If we are good, I will let you work on question 2. This is my favorite question. You don't really have to do much for 1 and 2. Just think about it intuitively. Like think about the meaning of what does each random variable represent. Don't think of it mathematically. Think of it like just in plain English. And then for part 3, it will involve a bit more math. You will want to use conditional probability here to derive the formula. I will give you 5 minutes and then I will take it up. Okay, let's look at this together. For part one, they want us to give explanation for why this distribution is true. Okay, I see a long answer here. Hopefully that is correct. So the students say that because if they are the same probability, it is like the same as running one big trial and selecting X and Y. And since the binomial n plus m, p is just summation, we are just adding them together. There's nothing that could break the addition. Okay, that makes sense. And x minus y doesn't work because you can't run a negative experiment with negative n or negative m picks. Taking y out leaves x as a mostly meaningless value and not a binomial. It also could end with a negative number, which I don't think possible in binomial. Yes, is a valid point. So what the student essentially want to say here is x denotes the number of success in n trial. So here you have n trial and probability of success in each trial is p. Then the number of success is denoted by x. Number of success. And here is n trials. Similarly for y, because y follow the same thing. So you also have n trials. And then y denotes the number of success here. If you take x plus y, you're essentially taking the number of success in these n trials plus the number of success in these n trials. Then what do you get? You get the total number of success, right? Out of how many trials? You have n trials here and you have n trials here. So is a total number of success out of 2n trials. Sorry, yeah. I got mistake here is m trials here. So the total number of trials will be n plus m. So it's the same thing, the total number of success out of n plus m trials. Therefore, x plus y is number of success in n plus m trials. Therefore, it follows a binomial distribution with number of trials is n plus m and probability of success in each trial. Here, probability of success in each trial is p. And here, probability of success in each trial is also p. So probability of success in each trial for every trial in this n plus m is also p. So that's why this holds true. And for part two, the student answer is correct when they mention about the negative value. If we think about it, x is a number of success here. Y is a number of success here. What if x is 0? It's possible, right? It's possible that you have 0 success. And then it's possible that y is something greater than 0. Let's say 1. Then in this case, x minus y will be negative 1, which means the possible range for the random variable x minus y, it can contain a negative number. However, for binomial distribution, it cannot be negative number. Why is that? Because again, if we look at the definition, the number of success in n trials is what the binomial distribution represents. And the number of success cannot be a negative number because when you count something, you cannot count negative. The minimum value you can count for the number of success is 0. But x minus y can take on a negative number with positive probability. So x minus y cannot follows a binomial distribution. Let me know if whatever I say just don't make sense to you, because all of these things, you are not really expected to know statistics in order to understand it. is pretty much the normal logic. The last one, we want to find probability of x equal k given that x plus y equal j. If we apply the conditional probability formula, we have x equal k and x plus y equal j divided by probability that x plus y equal j, like this. One of the common mistakes that the student make here is they break down the numerator into probability of x equal k times probability that x plus y equal j. However, this is wrong. Why is that? Because you're assuming independency between two variables, x and x plus y. You're assuming that this one and this one are two independent events. That's why you apply probability of AB equal to product of probability. However, this assumption is wrong. How do we know that? Because we ask ourselves question, if I know some information about x equal k, does it tell us anything about the information that x plus y equal to j? Yes, it does, right? Because if, let's say, j is 2 and k is 3, if we know that x equal 3 is true, then it tells us that x plus y equal to 2 cannot happen. So x and x plus y, they are not independent random variable. So we cannot use this formula. So what will we do about that? The questions say that x and y are independent random variable. So instead of writing it as x and x plus y, we can change and somehow write it as something x and then something y, right? Then in that case, you will have them multiply together. That's okay because they are independent random variable. How do I turn x plus y equal j in terms of y? How do I rewrite it in terms of y? Any guesses? Yeah, that's correct. If we have x plus y equal to j, then we have y equal to j minus x, right? And what is x here? We are considering x equal to k, right? So it is the same thing as saying y equal to j minus k. These two events are equivalent. X equal to k and x plus y equal to j is the same as saying x equal to k and y equal to j minus k. Divided by this one. Okay. And now since x and y are independent, I can just use product of probability. And then here we want to remind ourselves x follow a binomial distribution, n trials and probability of success is p. Y follow a binomial distribution where you have n trials and then also p. X plus y, as we did in part A, is binomial distribution, n plus n trials, and then also p is a probability of success. So now we can easily find these values. We have n trials. Probability of success in each trial is p. What is the probability that we have number of success equal to k? So out of n trial, I choose k trial to be success. And then I apply probability of success to K trial, and then apply probability of failure to the remaining trial. So I have Q here equal to 1 minus P, which is probability of failure. Similarly, here you have N trials and you want J minus K success. Here I have plus K because I have N minus J minus K. So it is the same as N minus J and then plus K. The last one, we have N plus N trial. And we have J success. Okay, let's see what we are having here. So here we have P to the power of K, and then P to the power of J minus K. So that give me K plus J minus K, which is just J. And then for Q, I have N minus K plus N minus J plus K. These two will cancel out, and we are left with N plus N minus J. And we also have this coefficient here. And we see that numerator and denominator, these two cancel out. And we are left with N choose K, N choose J minus K, and N plus N choose J. Does this look any familiar to you? Yes, this is hypergeometric, the PMF of hypergeometric. So that means this random variable follows a hypergeometric distribution. And if you think about it, it actually makes sense because what it's saying is, okay, X is the number of success from here, Y is the number of success from here. If we know that the total number of success is J, which is like we take J ball out of the two bins, then what is the probability that K balls will come from the first bin? Like, what is the probability that we have K success from the first N trials if we know that in total we have J success in total? So it's actually matched with the description for hypergeometric distribution. If there is no other question about this one, I will move on to the next question. Let's see. I will give you 2 minutes to read the question and then I will pick it up. So here we are given that the average rate of raindrops per square inch per minute is 20. When you see some events that they give you the rate over some time interval, it's likely that is Poisson distribution. Why is that? Because Poisson distribution is used to approximate binomial distribution, where you have very large number of trials and probability of success in each trial is very, very small. So what is our trial here? You can think of it as like millisecond or like something even smaller. If you consider each millisecond as one trial, then over 1 minute, you will have many trials, right? Like many trials. And then the probability of success, which means the probability that you got the raindrop over that region in 1 millisecond is very, very small. So that's why this can be represented by Poisson distribution. And we want to compute that the probability that this region, the region of 5 square inches, has no raindrop in 3-second time interval. So if we denote X as the number of raindrop over 5 square inches region in the 3-second interval, then what we are interested in calculating is probability X equal to 0. Probability of no raindrop, which means number of raindrops is equal to 0. And then we know that X follow a Poisson distribution with parameter lambda. And what does lambda represent? Lambda represents the average number of raindrop over 5 square inches over 3 seconds. So we have to find the average of this. And we are given the average rate per square inch per minute. But we want 5 inches and per 3 seconds. So first we will find the number of raindrop, let's say per 5 square inches per minute. So we will have to take 20 times 5. Because everything else stay the same, just the area of the region is 5 times more, so we times 5. But then we want per 3 seconds. Here is per 1 minute, right? 1 minute is 60 seconds. So from 60 seconds to 3 seconds, we have to divide it by 20, right? I hope that I calculated correctly. And then I will have 5. So the average raindrop over 5 square inches per 3 seconds is 5. So lambda is equal to 5. And we want that X follow a Poisson distribution with lambda equal to 5. Then probability X equal to 0 is given by this formula. Now we just need to plug the number in. Lambda is 5, X is 0. So this is what we got. Any question about that? If there is no question, then it's the end of our tutorial. You should try to attempt this by yourself. I'm pretty sure it's just geometric and negative binomial. I will also post the solution for this, and I will have review session tomorrow morning, so you can attend if you're available. Otherwise, good luck on your exam, everyone.